All right, good afternoon, everybody. My name is Bhattacharjea, and I'll be presenting what's supposed to be a tutorial called Accelerated Signal Processing on Embedded Platforms, Paths Forward. And before I get started here, with a quick show of hands, can I see who has ever played with a single board computer? As it looks like the vast majority of everybody. Who here has tried to get GNURadio running on that single board computer? So I'd say it's almost the same fraction. So it seems that there's probably a lot of people in this room who've done some embedded signal processing on small platforms and low power platforms. So what I would like to talk about then is how you can do SDR on these small embedded platforms that are kind of hobbyist tools. We're talking about single board computers, little compute sticks, things that plug into your TV. We're going to talk about how you do real-time signal processing on these devices and using the CPU and the GPU. The CPU has been kind of covered by several people more qualified to talk about it than me, such as Nathan and talking about the Volt project, but I'll go over it very quickly. We'll talk about how you can use embedded GPUs and what the embedded GPU landscape even looks like, and I hope that you'll walk away with an idea of what tools are at your disposal if you'd like to develop signal processing applications on the GPU. And so then at the conclusion, we'll kind of go through the different APIs and the different tools that are available. So what are we talking about? When I talk about embedded SDR, I'm talking about these things. I'm talking about cheap hobbyist grade single board computers and sticks that you can go out and buy. This is 60 some of them out of a total count of 64 that are published on this website called hackerboards.com. They've updated that list of 64 devices to some 81, and their criteria is that they all have to be Linux compatible right out of the box with distributions widely available. So pretty much everything here has some kind of vendor or community provided Linux distro that runs on it. And I don't know, for bonus points, anybody see something they recognize, see their favorite thing here? Yeah. Odroid. Yep, BeagleBone Black's down there. Yep, there's Pi in the bottom corner there. So you'll see a lot of these have similar form factors too, because people ripped off like the Pi's form factor. They took the GPIO pins and the spacing of the Ethernet ports there. And the red Pitaya is not, and so the red Pitaya actually has a sampling ADC, and so it's a slightly different beast. What I'm talking about is trying to combine an off-the-shelf thing that just does the computing piece with some kind of RF front end and sampling device. So that could be one of the analog devices chips. It could be a combo of analog devices FPGA. And I see Bob there has a red Pitaya. So are you going to be around for hacking day? Yep. All right, we're going to be hacking with a red Pitaya tomorrow. There's other embedded computers that you might use in your living room that are Linux compatible. So I've shown a sampling of these. These are like super cheap devices. The compute sticks are based on the same Intel Atom infrastructure. These Guleek guys in the middle are also Intel Atom. And the Pippo and the Amazon box there are actually ARM devices. So I'll be focusing on ARM and Intel. Most of everything I talk about is also directly transferable to some of the PowerPC stuff that's out there. But ARM and Intel on embedded accounts for like 99% of this kind of hobbyist market. So when we talk about embedded ARM, these are kind of the players. You've probably heard of almost all of these guys. Some of these smaller ones, like I wouldn't say smaller, but Allwinner, Rockchip, and MediaTek, you find these in kind of low-end, very cheap devices out of the Asian markets. And they call their ARM technology by these various brand names or nothing at all. And you can see there that there's a sampling of the end devices these things appear in. All right, what else are we talking about? We're obviously talking about signal processing with the GNURadio. Now, I don't have the latest version of GNURadio, so I can't tell you how many microbalance this thing scores, but this is an example flow graph of something you might want to do on an embedded computer. It's kind of a 101 kind of thing. Say you want to do some FM radio transmission with the stereo subcarrier with RDS from scratch because you want to learn how to do it without using GRRDS. So we're talking about kind of learning and hacking type of applications. And of course, the other piece you need of what we're talking about is the radio hardware. So I've shown just a sampling of things you might use. In particular, I'd like to draw your attention to the top left corner. The RTL dongles are great for very cheap experimentation. Of course, Edis products are great B205 Mini is something that you may use, or the BXX Mini line, or something you may use for embedded applications. I've been interested in the AirSpy. I'm probably going to pick one of those up. It's supposed to use, I believe, a superhet receiver, so it gets some pretty good noise performance. Okay, and then you can put all this together in the following way. You can take a battery pack that charges your phone. It's a 5-volt USB battery charger. You can take your favorite single board computer or Intel Compute Stick or mini PC that runs an Atom. And you may need some extra stuff for peripherals. So this is a Anker USB hub. Plug in an RTL dongle, and away you go. You have 3 nodes in some kind of spectrum monitoring application, 3 nodes in a passive radar, a platform for experimentation, a test bed. You could red team what bad guys could do with these kinds of things. And all of these run GNURadio right out of the box, basically. For the majority of them, it's as easy as DNF install, yum install, apt-get install. And you can run with those, or of course you could have Philip help you with making the full embedded version. But a new foe has appeared, and that foe is real-time signal processing on the CPU. And in order to understand why this is your foe, you have to understand both signal processing operations that we want to do and the modern CPU. So the real-time signal processing operations we're talking about are things like modulation. This is multiplying by some complex exponential. Also, this may involve lookup tables in certain cases. We're talking about entropy coding, error coding, and encryption. And these operations are kind of heavy on bitwise operations. And again, lookup tables. You also we have the classical multiply add heavy operations. So these are your convolutions and FIR filters and IRR filters and FFT calculations. So these are tons of multiplications and additions. But the modern CPU is actually optimized for managing the flow of instructions and keeping all your pipelines full. And the reason I say this is because all the new features that have kind of come out over the last 20 years have been things like branch prediction, out-of-order execution, speculative execution, prefetching the caches. So it's all kind of geared towards keeping your caches and your pipelines filled, rather than really quickly doing multiply-add operations. But of course, the CPU manufacturers have seen this gap between what the modern CPU does really well and between what you need for, say, multimedia applications or encryption. So they have some specialized DSP instructions, and these are kind of the SIMD extensions that we've heard about a couple of times. I'm not going to delve into any detail here other than to just draw your attention to we have ways from lowest level to highest level to access those CPU extensions. And in GNURadio, we're already using Vulkan, so we have very well optimized and pretty well profiled and understood kernels for our signal processing applications. And no matter how you get there, you end up with SIMD code with any of these ways of doing it. So if you look at the second one, the use compiler features directly, this can be intrinsics, or it can be trying to use the auto vectorizer, your -03 GCC auto vectorizer. And if it does a good job, it does a good job. You end up with SIMD code, and it doesn't really matter. So I'm not going to spend a lot of time on how you go through optimizing this. My personal workflow would probably be to use -03 to get assembly and look at it and tweak it, because we've all seen, or many of us have seen and noticed that the compiler emits really goofy stuff. And so you can kind of tweak what it comes up with by hand. In the Vulkan project, we picked the best out of what's in Vulkan. But my question is, what about things that aren't in Vulkan? So there's other implementations and other things out there that do optimized signal processing operations. And so my recommendations for the community is to, and I kind of asked this as a question to Nathan the other day, is we should probably profile all of our kernels and publish the results on at least 1 or 2 reference platforms. Call it, Intel 4th Gen i7 or 5th Gen i7 or whatever, and 1 or 2 ARMs maybe. And that way we know where we stand compared to other projects. It could be possible to offer a Google Summer of Code or other type of Summer of Code project to have a student look at this and compare against other solutions. And the Vulkan project actually maintains a list of other projects that do similar SIMD acceleration. So it would be great to have somebody compile all this information together And most of these are open source projects here at the comparisons webpage. So we could potentially learn from what they have done or pull in their implementations wholesale. All right, so that was kind of the stuff that we already know about pretty well, is how to do embedded acceleration using STMD. What about the GPU? So I've kind of shown you some of, this is a very few of the vendors that are involved in embedded GPUs. So the Intel Atom has some, they don't name it under any of these three technologies here, but it's got an Intel GPU on it. All Intel Atoms have an Intel GPU of recent generations. The NVIDIA Tegra system on a chip product is a combination of an ARM core and a GPU, their custom GPU technology. And then in the ARM world, the two biggest ones are kind of ARM makes their Mali core, their Mali GPUs, and PowerVR is the brand name of Imagination Technologies GPUs. So it turns out these things power all sorts of stuff. I'll get to that in a minute, exactly what they're in. But instead of what they're in, there's the question of why are they there? So why does a single board computer or this phone here need an embedded GPU? Well, it's pretty clear that the vendors want to support multimedia applications. And this is kind of the killer app. We all want to be able to play games. We all want to be able to take a video and upload it to Vine or Periscope or YouTube immediately. And games are a huge deal. So I have the statistic that mobile gaming is expected to generate almost $37 billion in revenue globally. And we all know, of course, mobile is just the marketing term for embedded. So there's a very good use case for why they're there. They accelerate all these applications. All right, so what does a mobile GPU architecture look like? So here I kind of have ARM's public information about their product called the ARM Mali T628. You might know that this powers like your Odroid XU4 if you use that one. So aside from some load balancing and task management stuff, and you've got some memory management, memory mapping down here, and some caching, and some proprietary ARM stuff, you've got these shader cores. But unfortunately, ARM is very opaque about what these things are. Now, according to ARM, each shader core has between 2 and 4 arithmetic pipelines. What's an arithmetic pipeline? Does anybody know what's inside an arithmetic pipeline? I sure don't. It turns out that they publish that each pipeline contains X number of ALUs, but they don't tell you what X is. But they do tell you that each ALU works on 128-bit wide registers. So it's kind of your typical way of accessing it. If you've got 128-bit wide registers, then it can be accessed as 2 doubles, 4 floats, 8 half precision, 2 long ints, 4 regular size ints, 8 shorts, or 16 chars. And if you need more information about some of this, you can find it. It seems that each core is actually split up into 4 pipelines, and each pipeline has its 2 to 4 ALUs. So there's a good bit of ALU here, It's enough to do some significant signal processing. I apologize, maybe somebody's mouse jacked me. All right, there we go. So I'd like to tell you a little bit about this embedded GPU landscape now. As I did with the CPUs, I've kind of shown you the people who own the IP. So in this case, there's the IP holders of the GPU technology, and then they license that to people who make it. And a lot of times they only license it to themselves. So Broadcom only licenses their technology to themselves. Qualcomm does the same. But people like ARM Holdings and the Mali here license to plenty of other ARM manufacturers. Similarly with Imagination, the PowerVR kind of is in all sorts of stuff. And then there's some of the final products here of note are like iPhones, iPads, PlayStation Vitas, all sorts of Samsung products from using the ARM Mali, other Samsung products using the Vivanti Corporation's Vega line. So we've got these GPUs, and they are inside of our embedded products. So we want to use them to do our signal processing. So as before, I've laid out lowest level to highest level how you can access these GPU functionalities. But I've stricken write GPU assembly. And this is because none of the vendors, except for Intel and Broadcom, even publish their GPU instruction set. And none of them, including Broadcom and Intel, provide you an assembler. So even if you go look up the instruction set and you know all the mnemonics and you write your great Intel GPU assembly, Intel doesn't ship you an assembler that turns that into machine code. So that's out. The kind of two intermediate approaches are to use shading language code, which I'm going to talk about in a minute, or to use a higher level compute language like OpenCL or CUDA. And these are kind of the directions that we should probably go as a community, but I'll tell you more about that. And then, of course, there's people who've written all sorts of functions that are already GPU accelerated. And so you may try to leverage that as a first cut when you're doing your acceleration. So if you're going to be doing GPU programming for compute, this is kind of the world that we live in. There's the OpenCL ES API and the Vulkan API. So these are both graphic-specific APIs that are compute-friendly. You've got OpenCL, which is designed specifically for compute on the GPU. And you've got NVIDIA CUDA, which is also specifically designed for compute on the GPU. But unfortunately, it only runs on like the two NVIDIA products that exist today. Let's see, I've got a couple notes here. There's another API called RenderScript that is similar and runs on the GPU, CPU, DSPs, all sorts of good stuff. However, it's part of Android, so it's not covered here, but maybe that's some work that can be done in the future to kind of port what they've done in the Android world. So if we start in the first top left corner of that previous figure, we're talking about GPU shading languages. In particular, on these mobile devices, the vendors all provide OpenCL ES shading language called ESSL for short. It's a C-like language based on the generic full-fat OpenCL shading language. So as an aside, the difference between OpenCL and OpenCL ES is that the spec for mobile is called ES, tacked on the end. There are these things called compute shaders that are supported on OpenCL ES 3.1 and up. And compliant vendors of that OpenCL ES specification have to provide compilers that give you machine code. So you start in this high-level C code, and you end up with GPU machine code. So as an example, I've showed a very simple compute kernel that runs on the shaders. There's a good bit of boilerplate. You have to set up your 4 vector types. So this vector of 4 floats will automatically get stuffed into those 128-bit registers and STMD'd for you. Then I've set up some stuff that, well, I should say I followed along with a tutorial that shows how you take 2 of these and create a structure out of them. So this is going to be for a vertex and a color. So we're still talking about primitives that are for graphics, but they can be used for compute. You have to go through some rigmarole to talk about alignment and memory. And then the magic happens over here in the main function. You write one main function, and you do some calculations. So here we're doing, you can see it's like some transformation, right? You're multiplying a radius times sine of an angle and cosine of an angle. So you're spinning something around. You could conceive of using code that does this to like calculate your complex phasor that spins around. So your e to the j omega t type of function. Okay, so there's 2 compute languages. There's OpenCL, as I talked about here. Aside from this, so we've got shading languages. That's kind of a weird approach where you're trying to shoehorn graphics primitives in. There's compute languages like OpenCL. So these are 2 languages based on C and C++. There's various operating modes, and in the interest of having some time for questions later, I'm not going to tell you much more about these other than to say you can either ship source code to the person using your OpenCL code, or you can choose to not, but then you lose portability. So you can kind of pre-compile it for a specific GPU target, or you can just ship C code or C++ code. And so I believe that's like what Phosphor does, is everybody gets the C or C++ code that gets compiled into your GPU code. And it requires hardware vendor support, and at the time of writing, it's broadly supported on all GPUs, except for NVIDIA mobile GPUs. And if you have a question about that, I'll clarify that afterwards. If you are using NVIDIA products, CUDA is the way to go. I'm not going to harp too much on this because Seth has talked about it previously. But yeah, it's a C C and C++ and Fortran-like language. There's 3 variants that you can use that get compiled into optimized GPU machine code. I'm going to skip these couple of sides. Okay, and then we have another graphics API called Vulkan. And Vulkan's kind of the successor to OpenGL, and it also supports these compute shaders. So you can write things that take sines and cosines or square roots on each of one of those ALU cores, and the Vulkan environment will parallelize it for you. It's supported by everybody except for Broadcom, so this is a decent option if you like thinking of graphics primitives. Unfortunately, it's really verbose. So I tried to follow along someone who was copying allocating 2 buffers in the GPU and mem copying one to the other, and it takes over 600 lines of code. So there's some 597 lines of boilerplate to get that going. So it's not the greatest option right at the moment. You can try to integrate your GNURadio with these GPU accelerated APIs. So we've heard about how TensorFlow can use CUDA under the hood. There's all these other technologies out there, ArrayFire, Magma, Kula tools. I'm just kind of putting these up there so that afterwards, when you're at home with the slide deck, you kind of have a set of references of things to look up and look more into. Also, I will say that most of these target CUDA. Even the ones that target OpenCL are kind of designed for AMD desktop GPUs, which support OpenCL, not for these weird embedded GPUs. So your mileage may vary. It may be that these implementations are not very good at all. I've not tried out any of them in much detail other than the ones that run on the NVIDIAs, because the TK1 is available where I work. Okay, so the embedded GPU paths forward then in our community. If you're trying to use the Broadcom video core, which is like Raspberry Pis, assembly is the only way to go. I know I struck that out right off the bat in that first one, but somebody did write an assembler for this one. The Raspberry Pi is kind of an oddity. It's kind of a one-off because Broadcom doesn't sell their products to other vendors to make single-board computers out of. But the moral of the story is, if you're on anything that supports OpenCL, which is everything except NVIDIA, use it. If you are on NVIDIA, go ahead and use CUDA. And that's basically what this slide says. I mentioned the Pi Video Core Assembler. And I will say that there are some products out there that'll take your CUDA code and turn it into OpenCL compliant C and C++. So you could, if you want wide support, you could do that. You could start with CUDA, use that on any NVIDIA GPUs, and if you need to work on a ARM Mali or something else, try to use some of these auto-converters. I've named a couple of them. I believe one of these was developed at Virginia Tech called CU to CL. There's another one called Swan. And so my final thoughts are that you can't pick up an embedded device and get optimal signal processing performance. And we've seen this over and over again, that we have an application, we try to run it on even like the E310's ARM, and it can't, GNURadio can't keep up. So there's still software work that needs to be done to leverage the processing power of the GPUs and the various SIMD technologies. I've got these kind of questions, and we've kind of beat this dead horse a good bit. So the answer to that one there is I think patches are welcome. So maybe there's some of us out there that can get cracking on improving, or even making 1 or 2 kernels for Vulkan, showing that they can improve performance on some small embedded platform. And it's an exciting time to be an embedded SDR. The vendors have kind of taken all of the chips that go in these things, and they have made millions and billions of them. So they've kind of spread out laterally over the market, and they give us stuff like the compute sticks, and they give us stuff like the Raspberry Pi. Broadcom's original model was to sell that to phone manufacturers, but the Raspberry Pi Foundation ends up buying all of them that they produce now. And you can realistically learn all this stuff now, that's SDR and signal processing, with practical hands-on experience for the price of a drink at a nice restaurant. A Pi Zero is $5, an RTL dongle is $10 on Amazon for the lowest end one. And so, if I get like a whiskey in Atlanta, it's at least $15. So yeah, that's about all I've got. I'd like to acknowledge my primary sponsor on this is Ben Riley, formerly of the Department of Defense, now at GTRI, for funding portions of this work. And I'd like to thank you all for your time.
Excellent. Oh, hands going up everywhere. Fantastic. Okay, Sylvain and Moritz.
Hi. So as options, you pointed out the OpenGL compute shaders,
Yes.
but those are not available on most of the very low-end card. I mean, you need as you said, OpenGL ES 3.1, I think.
Yeah, so they have to be 3.1 compliant.
Right. And like Raspberry Pi and stuff like that don't support that, but
Yes, that's right.
there is also the option of just using pure OpenGL. Just because the GPU think it's geometry doesn't mean it has to be.
Right.
And that's an option that is actually interesting too. It's kind of hackish, but if you want to target those $5 boards.
Yeah. I was kind of I was thinking in terms of what's kind of available today, and the vast majority of what ships today does support OpenGL ES 3.1 for those compute shaders. But you're absolutely right, you can just use OpenGL. I should do a survey of kind of these and see what supports it and what doesn't.
Yeah, actually that's something I've looked at recently. Unfortunately, a lot of them don't actually support.
Okay.
In the cheap ones, I mean.
Sure. Thank you.
Yeah, another thing to point out, like you had this all the vendors and
GPUs or CPUs? This one? This is CPU.
No,
vendors.
the GPU one. And another interesting thing, like we're all like open source guys. Some vendors do a better job at like providing you a sane image to work off, and like others don't. So I think that would have been an interesting data point also to have.
Yeah, so who provides you good tools?
Like Intel, for example, has been traditionally very good with their graphics drivers on Linux.
That's right.
And like ARM is traditionally terrible, so.
Is that a personal bone you have to pick, or?
No, just I feel like when you pick one of the small board computers, it might be interesting whether you end up with like a terrible vendor kernel, and that's like from the Stone Age.
Yeah, okay, so for kernel support and kernel versions, right, some of these smaller guys, yeah, so right, they actually license their IP to these guys. And so when these guys ship their final products, especially these guys, some of MediaTek and Rockchip, they might be running like a 2 version, 2.7 line Linux kernel or something like that. That's absolutely a good point.
Okay, we have more questions. Tom.
Another comment about the support for OpenCL and all those things. That's definitely true, but on Android, there's no more OpenCL. So if you're ever going to convert to Android, they've basically removed all support for OpenCL in Android. Basically, they're trying to get their render script as the way to do that. Secondly, when you started off, talking about the statistics benchmarking of all these embedded compute systems and Vulkan and all that stuff, it strikes me that seems like a really cool project for like a research institute somewhere, maybe down south of the U.S.
It seems like an interesting opportunity for a new DARPA PM to fund something.
Boom. Touche.
No, I mean, that's the perennial thing, right? A lot of this stuff is done on IRAD. Like, this has come out of another reason we had to analyze the embedded computer and SDR market on IRAD money. So, yeah, no, I would love to, right? I mean, I kind of geek out about this stuff and dig really deep into vendors' documentation to try to figure out what we can do on these different platforms.
Okay, let's have one more question over there. It's the only hand that's up now, and then we'll take it to the coffee break, to the whatever break it is, afternoon break.
So my first attempt using the CUDA in the Tegra, it just took a lot of time to figure out how to get the performance I was actually after. Have you kind of compared like who's better at helping you get the performance and who's better with profiling tools and stuff like that?
My gut would tell me that NVIDIA is so much farther along in this game of doing compute on their GPU. Their tools are much more mature. The CUDA driver is much more mature. And it's not fragmented like this ecosystem is, right? There's all these various other vendors that kind of all target the ARM CPU. But I don't have a firm sense of that. And I asked the same question basically of Nathan, right? What do we know about the CPU, and how do we know that our machine code is actually keeping the pipelines full and optimally running? And I'm not very familiar in the profiling tools, and I haven't delved into that level to kind of understand how do I eke out that last couple, hundreds of flops or thousands of flops of performance out of the CPU or the GPU. but my gut tells me NVIDIA.
Okay, so we'll have a 15-minute break now. So 4:45, we'll get back. We'll reconvene here. Thanks again to Raj and all the other speakers, and see you in a couple of minutes.